So Elizabeth Nadelman is with Janney Elstner. She's going to be talking today along with her co-authors, but on condition assessment of bridges in the United States. I think it should be a very broad topic. We look forward to hearing from you. She's in the Northbrook, Illinois headquarters office. So thank you for giving your talk.
Thank you for the introduction. As Larry mentioned, I'm Elizabeth Nadelman. I'm a materials engineer at Janney Elstner. And being a materials engineer, I have a unique interaction with NDE technologies. And so I'm going to present some of the ways that I use NDE in my particular practice. You'll notice my co-authors are Mohamed ElBatanouny, who does a lot more NDE work, and then Todd Nelson, who's another materials engineer. So I'll start by talking very broadly about some materials distress that we might see in bridges, and then get into some specifics about NDE methods that I use to evaluate materials distress. These include things like visual assessment, delamination and void detection, corrosion condition assessments, and other techniques, but those are the three that I'll be primarily focusing on. And then I'll follow it up with some recent project examples. But actually throughout the entire talk, I'll be providing examples of where we use these specific techniques, and so hopefully it provides a little bit more context for the particular applications I'm talking about. So just to present a brief overview of some materials-related distress mechanisms in concrete bridges, probably the most common that people see are cracks. And cracks can have a variety of sources. You know, transverse cracks can maybe be representative of shrinkage that takes place or a thermal change. You can have map cracking that might indicate ASR or some other material distress. There could be plastic shrinkage cracking and so on. So there's a lot of sources for cracks, but that's probably one of the most common materials-related distresses that we'll see in concrete bridges. There's also delaminations and spalling, again, very closely related to cracks in many cases, often an indicator of some internal distress, perhaps corrosion of reinforcing steel. On the surface, we might see efflorescence or corrosion staining. We might see evidence of scaling, particularly in environments where freeze-thaw is popular, and pop-outs as well in freeze-thaw environments. And there's other types of materials-related distress that we'll commonly look for and see in bridges as we do these evaluations, but these are probably the most common that stand out. Now, I mentioned before there's a lot of materials-related distress that we see, but they're often associated with particular materials problems. And as a materials engineer, that's sort of what I'm trying to do, is figure out what's actually causing the distress that we're seeing. And so I use NDE techniques in my particular applications to help me shed some light on the particular underlying method or mechanism that's causing the distress. So, for example, if we see shrinkage, take shrinkage as a mechanism as an example. Cracks are probably the most common because if something that's restrained wants to shrink, the tensile stresses are eventually going to result in cracks. But we might also see evidence of efflorescence on the surface. Perhaps there's cracks that formed and then salts get applied to a bridge deck, for example, and on the underside, we'll see signs of efflorescence. If we talk about corrosion of reinforcing steel, obviously corrosion staining is going to be a big indicator that might be happening. But some other mechanisms or other distress indicators we might see would be cracks, delaminations, and spalls. And I also have a check mark here next to efflorescence, because if we see signs of efflorescence, evidence of salt buildup, that could also point to corrosion as a particular mechanism, even if we don't see corrosion staining or cracking on the surface. For freeze-thaw distress, probably the most obvious ones on this list would be scaling and pop-outs, but we can also have freeze-thaw distress that leads to cracking and delaminations. Alkali-silica reaction, or alkali aggregate reactions more broadly, very characteristic cracks with efflorescence. And then there's other materials-related distress mechanisms that we might see as well. So when I use NDE methods, there's a few different ways that I'll use them to evaluate materials distress. Today I'm going to just focus on 3 of the applications. This is not an extensive list, but it's probably the most common applications of NDE methods in determining the cause of materials-related distress. So I'll talk about visual assessment, delamination and void detection, and corrosion condition assessment. For visual assessment, this is the most common and probably the simplest of all NDE techniques. Doesn't require any specialized equipment, but it's perhaps the most complex as well in terms of figuring out what's causing a particular materials-related degradation issue. So when performing a visual assessment, things that we're looking for are what features are present. Are there cracks? Are there spalls? Are there delaminations? And so on. For each feature, where are they located? We might want to make a map of them. What size are the features? What orientation and shape? And then once we map everything out and sort of look at it holistically, is there a pattern to the distress that we're seeing? If we see a lot of transverse cracks like I've shown in this figure, that might lead us to think more about some sort of movement of the concrete, whether it's related to thermal movement or shrinkage of the concrete. If we see maybe more random map cracking in sporadic areas, we might think of some other type of distress mechanism instead. So the pattern is also really important to helping identify what's the underlying problem. One thing that often gets overlooked when we talk about visual assessment, we frequently show photos of people looking at the tops of bridge decks, but looking underneath bridge decks is also really enlightening in terms of understanding certain materials-related distress problems in concrete construction. So, actually, going back to this photo, I have a picture of Todd over there taking a look underneath this bridge deck, and he's taking a look at the cracks and the efflorescence in the cracks. It might be a little hard to see, but I'll show some photos of it later on. There's a lot of cracks, and you can really see them very visibly from the ground because of the salt and the efflorescence that's built up on the surface. But what happens if you have difficult time accessing the underside of the bridges? It's still really valuable information, and so there's a couple ways that we can get about that. One is to use aerial lifts or a snooper, for example, some sort of device so that you can physically be transported underneath or to a difficult access area. And so here's a picture of someone performing a visual assessment on the underside of the 3rd Avenue Bridge in Minneapolis. But we also have been using some more advanced options, which is UAV or unmanned aerial vehicle assisted visual assessment. So this is one of our many UAVs or drones as they're commonly referred to. And we have attached to it a very high resolution camera that we can actually rotate so that we could see above or see the top surface or see the bottom surface depending on how we rotate the camera angle. So for that bridge that I showed the picture of before, where it was over a very steep ravine with a river underneath it, we actually used the drone and went underneath it. And you can see very clearly in very high resolution where all of these cracks are forming, transverse cracks. So using this image or this technique, we can very quickly scan the entire length of the bridge deck, see where the distress is the greatest, maybe help identify areas we might want to survey more intently from the top surface. And one other really nice thing about this is we get the really high resolution images, and so we can start looking for very fine details about what might actually be going on in terms of the cracking, which I'll show at the end of the presentation in one of these applications I talk about. Another cool feature about our particular set of UAVs is that we also have the ability to use infrared camera. And so infrared can help us see some cracks a little bit more clearly in this case. And I'll show later on we can also use it to detect some delaminations and voids in the concrete decks. So the most common methods of detecting delaminations and voids are either hammer sounding or chain dragging. Both of these are manual techniques, and so got to require you to listen up really intently and hear. Took me a while to get my ears trained, but I can now hear delaminations, at least, not quite just the surface delaminations. I can start hearing them deeper, but it takes some time to get your ears calibrated to hearing these particular features at times. And sometimes it's just difficult to hear altogether. So we like to also use some advanced techniques. Certainly the chain dragging and hammer sounding are excellent methods for surveying, especially chain dragging will help us allow us to survey very large areas pretty rapidly. And hammer sounding has excellent applications for very small focus studies. But some of the other methods that we can use to detect delaminations and voids would be ground penetrating radar, or GPR, infrared thermography, like I mentioned before, and some more advanced methods like impulse response, impact echo, ultrasonic methods like UPV, and shear wave tomography. In the interest of time today, I only plan to talk about the GPR and infrared thermography applications, but in our firm, we have used all of these to investigate bridge decks in some capacity, or bridge structures in some capacity. So ground penetrating radar uses a high frequency electromagnetic wave signal and basically uses the way that that wave is reflecting off of the features inside of the material to get information about the subsurface. So this might be a typical scan from a surface of a bridge deck. In fact, this is a scan from the surface of the bridge deck I had shown previously, where we're scanning over a horizontal distance and we can see certain features with depth. So just to interpret this sketch or the schematic, we see at the top, the very top of the bridge deck, this black feature here shows us where the bottom of the deck is. This is not a straight line. It does sort of wiggle, so it shows that there's a little bit of non-uniformity in the deck, but they actually did a pretty good job of getting it more or less in the construction tolerances in this particular structure. These parabolas here are what happens when the radar interacts with the reinforcing steel. And so we can use these signals to locate the tops of the reinforcing steel, get information not only about the spacing of the reinforcement, but also the depth. Now, if there were delaminations or voids in the concrete, we'd have a signal sort of similar to what we see at this bottom of the deck, but it would be shifted up to a higher plane. And so we can use that to see where these delaminations and voids might be. We will sometimes do larger area scans with radar and use that to come up with maps of where the delaminations are located. We can also make maps of where all of the reinforcing steel is located, which is very useful for service life evaluations and other material investigations. But just talking about delaminations and voids, we can use this area mapping technique to come up with maps of where these delaminations are located and their approximate depths. The other application I mentioned before is infrared thermography. So basically what the reasoning behind this is the cracked voids and delaminated concrete have different thermal radiation that they emit relative to sound concrete. And I'll show that in another slide. We can use that to identify where cracks, voids, and delaminations are. So this is one of the bridge decks I had shown previously. We've got our UAV and it's got an infrared camera on it. And so I showed this picture previously where we could see the crack. The reason why the crack is visible is because we actually took this as the sun was starting to set that particular day. So the concrete internally was very warm and the surface was cooling off. Normally you have to do it where there's some sort of temperature contrast, either in the morning where the concrete might be cool and the top surface is just starting to warm up, or later in the afternoon where the concrete's warm and the surface is starting to cool. But because it was warm earlier in the day and then the surface started to cool, these cracks really started to stand out quite a bit. It also let us map or image the bridge deck in other ways. So you can actually see these are the girders and the beams on the bridge. You can see them reflected through the bridge deck because of the different heat signature. But up here in the corner, you can also see we found a delamination, and we actually had detected that by other methods as well. So the last one I want to talk about is just some corrosion assessment techniques that we'll use. There's three main corrosion assessments that we'll often do in the field to determine causes of material degradation. Probably the most robust one that we use on just about any type of structure is a half-cell potential measurement. And for concrete, we'll also do concrete surface resistivity measurements and corrosion rate measurements, either with contactless electrical pulse response analysis, or CEPRA, or linear polarization resistance, LPR. So the basic concept with the half-cell potentials, it's an electrical method that you can use to detect areas of active corrosion that have just not resulted in delaminations or spalling yet. So this is really powerful because up to now I've been talking about distress of concrete that leads to visible signs of deterioration. But when we're talking about corrosion condition assessment, a lot of times what we're looking for are the invisible signs of deterioration. So understanding what's actually going on inside the concrete, inside the steel, that hasn't resulted in visible signs of distress is really important. So this is a schematic that's taken from the ASTM standard. This is ASTM C876, and it talks about how to conduct half-cell potential measurements on reinforced concrete. What we'll do is we'll often take surveys with half-cell potentials. We'll measure them on a grid, either using these individual single electrodes here, take a point measurement, or we'll do a rolling measurement like I've shown here, where we'll actually roll a wheel that has inside of it a half cell, and we will map and make contour plots of how the half cell potentials are varying over a particular area. And so this one's just shown very schematically. The redder colors are potentials that are less than minus 350 millivolts, so this indicates a high probability of corrosion. Green and yellow are areas that are either low or moderate probability of corrosion. So you can see for this particular column, there was quite a bit of corrosion activity happening at the top of the column. And even though we couldn't actually see it, once we went back and did some sounding in the area, we actually heard some very faint delaminations that hadn't managed to break the surface. But we didn't see any evidence on the surface of corrosion, but it was certainly there when we measured with the half-cell potentials. Another method that we'll often use is surface resistivity. So surface resistivity is a method that we can get an electrical property of the concrete that's correlated with conditions that promote an increased risk of active corrosion. Surface resistivity does not tell you that you have active corrosion or not. It just tells you that you have conditions that if your concrete or if your steel is actively corroding, it could be corroding at a higher rate. And so the way we do this, we put a 4-point probe on top of the concrete surface. There's a current that flows through the outer two probes, and the voltage is measured inside. Using Ohm's law, we can calculate resistance, and then use that with some geometry correction factors to calculate resistivity of the concrete. And again, there's ways to interpret what this resistivity means in terms of, is there a risk of there being a high corrosion rate or a low corrosion rate? Similar to surface resistivity is the CEPRA technique. Just like CEPRA, it applies current through the two outer probes and measures a voltage response on the inside. Unlike resistivity, the way that this works is it applies an alternating current signal and it varies the frequency. And so the material, if the steel is corroding, the response of the material at different frequencies is going to be different than if it is, it's going to be different if it's corroding than if it's not corroding. And so the equipment can estimate the corrosion rate based on the particular signal that is resulting from this particular measurement. And there's another way we can get corrosion rate measurements, and this is linear polarization resistance. Essentially what we're doing with this technique is we're applying a potential shift to the steel. So we have an actual connection to the steel. We apply a potential shift and measure the resulting current. The current that results is going to be proportional to the rate that the steel is corroding. And there's ways to interpret both the corrosion rate by linear polarization resistance and also from the CEPRA measurement. So I just want to wrap things up by talking about a couple recent project examples. I'll talk about bridge decks that we did some investigations on in Montana and some bridge piers that we're currently evaluating in Nebraska. So just as an example, there were 22 bridge decks in western Montana that were experiencing pretty advanced deterioration after only 2 to 10 years of service. So distress was characterized by very, very frequent transverse cracking. Again, very easy to see that because of the efflorescence in the cracks. And in certain locations, the cracking was so severe and advanced that they got through holes through the concrete, so you can actually see daylight through this. And keep in mind, these are only 2 to 10 years old, so very advanced deterioration, pretty surprising. So we actually went out there and did quite a bit of condition assessments. We used the UAVs to do a visual survey in addition to our own human eyes. We also used the UAV to assist with a delamination survey, as well as performing some chain drag and hammer sounding. We used quite a bit of GPR to figure out where the reinforcing steel was located, and what ended up being pretty important for this particular project was the cover, which ended up being almost 3 inches. We did some impulse response measurements to help, again, identify areas where delaminations had occurred. And then we did a lot of chemical and petrographic analysis of some cores that I didn't talk about here, but it helped us rule out other types of materials distress. But going back to this photo, when we used the drone, we could actually see quite a few patterns developing on the underside of the bridge decks. And this was a pattern that we saw repeatedly over many of the bridge decks that we looked at. So became very clear to us through several of these investigations that the cracks initiated pretty early on, right over the beams, and then started to progress inward, where eventually they'd come in pretty close contact and they'd sort of jump. So we started calling these jump cracks. And we actually found a jump crack on the bottom of bridge deck that we then found in the top. And when these jump cracks occur and where they become through cracks, that's where those through holes ended up forming in those previous bridge decks. So we did a lot of evaluation, eventually concluded that this was actually some very early thermal cracking, and helped Montana revise some of their project specifications to help avoid and limit thermal cracking in the future. But that's just one example where we used some of these advanced analysis techniques to help us identify causes of material distress. The other example, and this is still some ongoing work, but we're currently evaluating some bridge piers in Nebraska. There's 10 of them that we've done some in-depth evaluations of, but there's several overall. They've been in service for 48 years, and they have varying levels of corrosion-related distress. I'm showing in this picture the most obvious one with quite a bit of spalling and corrosion on the surface and a lot of moisture staining and cracking. There were some that were completely opposite of this pristine condition. You'd never know that they were 50-year-old concrete. So varying levels of distress. So we performed several assessments over several days. We did visual surveys, we did delamination sounding, half cell surveys, surface resistivity measurements, measured corrosion rates, looked at the reinforcing cover, and so on. And again, did some chemical and petrographic analysis of the cores. And through this work, we were able to identify areas of these piers that had higher risk of corrosion than others. And so it helped us to go back, look at these piers at those locations where we were measuring high corrosion rates and high corrosion activity and figure out what's causing it. Is it an exposure issue, maybe a leak that's happening, something that might not be visible, perhaps influence of a prior repair on the bridges, and so on. And so using all of these techniques, we were able to get a much bigger and broader picture of the current state of these bridge piers and make better informed decisions about how that material is going to degrade over the future. So just to summarize, there's a variety of NDE techniques that we can use to identify and troubleshoot materials-related distress problems in concrete bridge structures. And it's not just a single technique that we'll use. We often rely on a variety of tools to get the complete picture of what's going on. And these emerging NDE technologies like the CEPRA, LPR, and the UAV usage are really just more tools to put in our toolbox to help get a more complete picture of what's going on. So with that, I'd like to thank you for your attention, and hopefully I can answer any questions you might have.
Two very short questions. Do you pilot the drones by hand?
I personally do not, but we have a number of trained drone pilots in just about every office that we have across the country, so several of our staff can pilot them.
Certainly drones are being increasingly used by people. So, anybody else have a question? Well, thank you very much. Oh, there's a question.
What was that white staining coming from the horizontal crack?
Yeah, so that's efflorescence, and there's a couple sources efflorescence can have. One is what you're probably thinking of where it might be ASR. What these actually were, it was the salt buildup from the brine that they applied to the bridge decks in the winter time. And so it was just crystallizing on the surface.
Well, thank you very much.